So before we can understand how to do change of variables in more dimensions, let's go back and look at change of variables in one dimension and figure that out geometrically. Change of variables in one dimension is actually something you all know and love, and it's u-substitution. Whenever you do a u-substitution, you're doing a change of variables in one dimension, usually changing from the variable x to the variable u, where u can be basically whatever function of x you want. So for example, if we wanted to integrate from 0 to pi over 4 of sine 4x dx. And you might be able to do this without explicitly writing out the u substitution now, and that's fine. But the first time you did it, you wrote u equals 4x, and your hope was to not integrate sine of a complicated function, but to integrate just sine of some variable, because we knew how to do that. And so then du was 4dx, which means that dx was 1/4 du. And so then we could integrate, we could replace the dx with 1/4 du, and then we could replace the sine of 4x with sine of u. And then we could keep the bounds and then integrate and substitute in later, or this time actually let's replace the bounds. So when x is 0, u is 0, u is 4 times x, and when x is pi over 4, u is pi. And then we can finish the integral. Let's look geometrically at what this is. So this top curve is y equals sine x, or maybe y equals sine u. And what this says is I know how to find this integral. The area under the curve from 0 to pi, here's pi, of the curve y equals sine u. I didn't know how to find at the beginning this integral, which is the area under the blue curve from 0 to here's pi over 4 of sine 4x, which is the blue curve. So I'm just going to find the red curve, and then I realize from this line that my space, every time I go up a little bit in x, I'm going up 4 times as much in u. So my space is stretched out by a factor of 4. So there's what this fraction 1/4 is doing. It's fixing the area under the red curve to equal the area under the blue curve. It doesn't have to be area, but area is an easy visual thing that can help us understand this. Okay, so then what if we're doing something more complicated? And what if we're integrating from 0 to root pi of x sine x squared dx? Okay, and I haven't actually graphed x times sine x squared. I've just graphed sine x squared, and I've graphed sine x. So like what I'm actually doing, I'm not finding the area under the blue curve. I'm trying to find x times that, and from 0 to root pi is about 1.77, so it is about there. Let's see, if I multiplied this by x at 1, I would pass through, I would be at the same value. Everything below 1 would be smaller. Everything above 1 would be bigger, maybe not bigger by that much. So I'm actually trying to find the area under the gray curve. But I can, for ease of stretching, I can look at area under the blue curve. And again, I don't know how to do that. I do know how to find area under the red curve still. We'll call this sine u. But this time we have u equals x squared. So then du is 2x dx. So now I'm stretching by a weird amount. My interval 0 to root pi gets stretched out 0 to pi, but it gets stretched out non-linearly. I'm not multiplying by a factor of root pi. Every little thing I'm going up by 2 times whatever value on the x-axis I'm on. So that's weird. The space is getting stretched out non-linearly in this case. But my interval, 0 to root pi, every number there still gets mapped to an interval 0 to pi. It just might be that like this number, let's see, 2x. Okay, so every time we go up here, we're going up a smaller amount here. And then maybe over here, that thing maps to a much bigger portion of that interval, if that makes sense. All you really need to know is space is getting stretched non-linearly. And then we know how to find the area under the red curve. If we did that full u-substitution, you would end up with a 1/2 integral from, we're going to switch 0 to pi sine u du. You can check that yourself. So why do we multiply by 1/2? And there's a 2x here. So to get from red to actually no curve that's drawn here, you shrink it by 1/2. So what's actually happening? So there's this other curve. Let's see. Pi over 2 is about 1.5. So there's this other curve. And that's equal in area. The black one is equal in area to the gray one, because the gray one is the thing you're trying to find. Okay, so a little bit stranger stuff going on, and we're going to get even a little bit stranger still as we go into 2 dimensions.